Welcome to part 2. For part 2, we are going to use our definition of our derivative to find the derivatives. So we haven't done this since, August of last year in BC. So this will be kind of fun for us, right? Right. Okay, so we're going to use the definition of the derivative to calculate these partial derivatives. Use power rule and constants to check your work. So let's just do the derivative. Let's just do with f of x. The partial of f with respect to x. And again, if you want to write it this way, that's all right. So and if we take that partial derivative, ready? Remember, y is going to be a constant. The only thing we're looking at is the x. So this would become 2xy plus, take the derivative here, just becomes, well, x is my only variable. Y squared is a constant, so this would be like saying 5x. The derivative of 5x would be 5, so that just becomes y squared. And if I want to find the partial of the function with respect to y, again, if you want to write it in the notation fyxy, f sub y, again, nope, we don't put any primes anymore for partials. So I take derivative here with respect to y. This time x squared is my constant. So this is like saying like 5y. The derivative of 5y would be just 5. So this becomes just x squared plus, here, the x is my constant, so I drop my power on the 2. We get 2xy. So when we use our limit rules, we should get these two answered right here. So let's just find the partial with respect to x. Now, recall, we don't typically like to use delta x. We're going to let h equal delta x here. Alright, so let's see here. My derivative with respect to x is our formula. The limit as h goes to 0 of f of x plus h y minus f of x y all over h. So notice we're only messing with the x. The y stays the same, like it's a constant. So when I plug in, I'm only plugging in the x plus h for my x's. So when we set this up, we get the limit as h goes to 0. And this becomes, right, let's plug this in. We're going to get x plus h squared y plus x plus h y squared minus the original function x squared y. It's a plus, but we're subtracting, so we get minus x y squared over h. Doing a lot of algebra. Okay, let's see how fast we can do the algebra. I know that this becomes x squared plus 2xh plus h squared. Multiplying it by y, we get x squared y plus 2xyh plus h squared y. Distribute here, plus x y squared plus h y squared minus x squared y minus x y squared over h. And at this point, you're like, I thought we had numbers in math. Where did all this come from? But not to worry. Just like last year, anything that does not have an h in it, better cancel. X squared y, xy squared. And out of everything else, I can factor out an h. So the limit as h goes to 0, factor out that h, you're going to get 2xy plus hy plus y squared over h. The h's cancel. And if we let h go to 0, what are we left with? We are left with 2xy plus y squared, which is our partial with respect to x. Right there. And of course, you can do the same technique to get the partial with respect to y, but we'll let you guys do that one. We're just going to go ahead and move on to the next problem. Because the real question is, when would we ever need to use the definition, right, using the limit process. Well, let's take a look here. Back in single variable calculus, we never had to use this rule. Once we learned the tricks, the shortcuts, we could take their derivatives. But there are instances where we cannot take a derivative or find out what the derivative at a point is. And we really start to see this in multivariable. Let's look at the following function. F of xy is this. I have no idea what the shape is, but this looks kind of funky. This x cubed plus x to the fourth minus y cubed over x squared plus y squared. It has a value, xy, everywhere but 0, 0. And the reason that is because it would be indeterminate. This is indeterminate at 0, 0, 0. It has no value there because we get 0 over 0. But we have established a value, like we plugged in a hole. There's a hole there, dear Eliza. So we plugged in a hole by saying that it has a value at 0, 0. This problem cannot be solved using our power rule. So if I want to find the partials with respect to x, we cannot solve for this derivative right here at 0, 0 because it's at indeterminate. Even if we take the derivative, we would still get 0 over 0. And that's really kind of weird for us because at 0, 0, the derivative does not exist. So, but it does have a value there, and it does have a derivative. So we want to find out what that slope is approaching because we've given it a value. So we can use the shortcut derivative rules anywhere else. But if we want to find the partials at 0, 0 at the origin, we have to use the definition. So we're going to find the rate of change of our function z. Remember, z is f of xy, so we want to call it z. You can. With respect to x, and then find the rate of change with respect to y at the origin. So let's deal with the partial with respect to x. Now, a couple things to point out. We are going to need the value, so that's easy to get. The value when x is 0 and y is 0 is 0, so they're giving us that value. So, but now, if I'm looking at the partial of with respect to x, I'm not concerned about the y value. I'm really only concerned about the x value. So I'm going to rewrite my function as this, f of h, 0. We only care about the x value. We only want to see what's happening as x is changing. So I'm going to give x the letter h and let y be 0 at that point because that's our point anyways. And if I rewrite my function, this is going to become h cubed plus h to the fourth minus 0 over h squared plus 0. And that's going to leave me with the function h plus h squared. So this is our function as only x is changing at 0. Finding the partial then, I can write this now as the limit as h goes to 0 of, remember my rule, f of x plus h 0 minus f of x 0 all over h. Remember, the only thing we're interested in is the change in the x values. I'm not interested in a change in the y's. Those are always going to be 0 for us. So, and where did I get the zeros from? Again, my point. So we can recall that we're given the point 0, 0, 0, and I can even substitute here. Therefore, I know that x is also 0. So my partial rule would be the limit as h goes to 0 of just f of, let x be 0, f of h 0 minus f of 0, 0 all over h. And this is my rule I can use. So when I now take the derivative, the partial of x, that's going to become the limit, as h goes to 0. So everywhere my function, look at my function here, everywhere there's an x, I'm going to plug in h0, which we already did. That's why I did it up here. So this first part right here is just going to be h plus h squared minus, And if I plug in the point 0, 0 into my function, I'm going to just get 0 all over h. And what are we left with? The limit as h goes to 0, we're left with 1 plus h, and as h goes to 0, we get 1. Therefore, we can say the slope in the x direction at the point 0, 0, 0 is 1. Really kind of cool little problem right there for you. Now, of course, we did it for the partial with respect to x. You can do it with the partial with respect to y. I'll see you soon. Have fun. Bye-bye.